This is a video for BC calculus students. I'm going to be doing some problems on derivative of parametrically defined functions, right? It's a follow-along type of video actually. So once you see the problem on the screen, please try the problem first on your own and then unpause it to check your answer. And if you got totally lost, you can see how I thought through the problems. All right. So here's number one. What's the derivative of the parametric curve defined by x is tangent t, y is cotangent squared t? Okay, so hopefully you tried it. So it's asking for dy dx. So if we remember the formula is dy dt over dx dt. And how can we easily remember this? Well, if we think of the differentials as just like variables, the dt's cancel and you're left with dy dx, okay? So what's the derivative of dy of y with respect to t? That is just 2 cotangent x minus cosecant squared x. Don't forget the chain rule. Derivative of tangent is just secant squared, okay? So we start simplifying. Honestly, this is correct in itself, but if it's like a multiple choice answer question and you need to match answers, you might have to simplify. So I changed everything in terms of sine and cosine over here. And you can see that becomes minus 2 cotangent cubed t. Number two, find the derivative of the curve defined by x is 1 plus 2t and y is 2 minus t squared using two different methods. Okay, so we can eliminate the parameter. The parameter is t. We can write y as a function of x, actually. Okay, so we solve for t in the x equation. So t would be x minus 1 divided by 2. And therefore, we can plug this definition of t into our y. So it becomes 2 minus parentheses x minus 1 over 2 squared. And if we simplify it, it would be 2 minus a fourth times x minus 1 squared. Okay, so differentiate from here. dy dx is derivative 2 is just 0. Here we need the chain rule, so it'll become minus half times x minus 1 to the first power. Hey, that's one way. Method two, we can use that same formula as before. Dy dt over dx dt. So derivative of y with respect to t. Let's go back to here. That would just be minus 2t. Derivative of x with respect to t is just 2. So minus 2t over 2, which is minus t. Now, what is t equal to, though? We still need to use our definition to get that dy dx is minus half times x minus 1, because it's just minus of this. Okay, so this is, we found it in two ways, but we still needed to write t in terms of x, okay, in order to match the two answers. Technically, this is correct as well. If we're interested in the derivative with respect to y, derivative of y with respect to x in terms of t, actually, because t is the input per se. All right, problem three, find the second derivative when t equals 2 for the curve defined by x is e to the 3t, y is t squared e to the 3t. How do we get the second derivative? We need the first derivative first. So let's do that. dy dx is dy dt over dx dt. So what's dy dt? We need the product rule. That's right there. I'm not going to go over that. dx dt, we need the chain rule. Okay, so notice that we can divide by e to the 3t because it's common to both these terms, okay? And we can also divide by 3. So then we would get t squared plus 2/3 t, just to simplify. Now, the second derivative, by definition, is the derivative with respect to x of dy dx. This is by definition, okay? So we basically, if we use the chain rule, it'll be d dt, dy dx over dx dt. This is the chain rule. That's actually how we get this as well. Chain rule. Okay? As dy dx is dy dt times dt dx. And the dt dx we can put in the bottom of the fraction by flipping it, the reciprocal. Okay? So we do the same thing here. Similar here. Okay? So derivative with respect to t of this guy is just 2t plus 2/3. Okay, and then we need derivative of x with respect to t again, which is 3e to 3t. So this is our second derivative with this in terms of t. Okay, so now we want it when t is equal to 2, so plug in t as 2, you should get 14 over 9e to the 6th power. Problem 4. If a parametric curve is defined by this guy, x is this guy, and y is this guy, at what points or points does the curve have horizontal tangent lines? And at what points or points is the curve not differentiable? So it has horizontal tangents when dy dx is equal to 0, not differentiable when dy dx is undefined. Okay, so let's find dy dx. Okay, so dy dt over dx dt once again. The dy dt is just the power rule, right? It'll be t squared minus 2t minus 2. Dx dt, again, power rule, will be t squared plus 6t plus 5. Okay, so let's start factoring because we probably want to get zeros on top and maybe possibly zeros on bottom. Okay, so factor top, it's this. Factor to bottom is this. Oh, look, there's actually a kind of a removable discontinuity for this dy dx. But we still can't have t as -1. This is a domain restriction still, okay? Because we'll be dividing by 0, okay? So we can leave it like this, or we can simplify it like this, okay? This is actually more useful over here, the unsimplified form over here. So the horizontal tangent occurs when t equals 2, okay? And it's not differentiable at t is -1 and t is -5 because we'll be dividing by 0 at those two. And we have a 0 at t is 2, not at t is -1 because we'll have a divide by 0 problem. So it's not differentiable there, okay? So the corresponding x, y coordinates are these if you plug in the values of t into a definition, okay? All right, that's it for this video. There is a word problem that I didn't do it yet. Maybe that'll be a separate video where I'll stitch it along with this if I decide to do it right now. Please give this video a like if you found it helpful in any way, and hopefully see another video as well.